Hello everyone, welcome to the extension of the lab 4 in which we are going to compare various type of the FFT accelerator using the ACP and HP port. In the previous lab, we compared the performance of the ACP port and the HP port for a fixed burst size and the clock frequency. In the today's lab, we are going to play around with the DMA burst size, the clock frequency of the accelerator inside the FPGA, as well as the different memory mapped bus width. Also, compared to the previous lab, here we are going to use the latest version of the Vivado, which is 2022.2. So let's begin. So let's open the Vivado. We are using the 2022.2. Okay, so the Vivado process is more or less same. So we will start with the with the regular project creation. In the project creation, we will make sure that we use the appropriate folder. So we are going to use the zedboard as we did last time. Okay, so in the we will develop the block diagram from the scratch so that we can go through all the steps. Okay, so run connection automation. Here we will enable the cross triggering. Then inside the Zynq, we will enable the HP port. And inside the HP port, we will have the 64-bit of the HP port, and we will have the another HP port with the size of 32-bit. Okay, then we will have the ACP port. Here we'll have the ACP port. We'll enable the cache currency. Then inside the peripheral, we will disable the peripherals which are not needed. And inside the clock, we will generate a two clock, one with the 100 megahertz and then another with the 250. So let's say 240 megahertz. Okay, so now you can see that this is the warning which comes in the latest Vivado, but it should be fine. We don't need to worry about it. So now you can see we have ACP port, HP port, HP1, trigger in and trigger out. So for trigger in, trigger out, we will add the ILA. Okay, so now let's start with the actual one. So we will start with the DMA, first DMA. So we will call this as a ACP DMA, AXI DMA ACP. Okay, So for this DMA, we'll disable the scatter gathered mode. This 14 should be sufficient for the small size IP. Then we will have the 64 bit of the memory map as we did last time, and the bus size we will limit it, we'll use it as a last time. So 64, this should be 64, and this should be 256, and we enable the unaligned transfer. Okay, so we are using the ACP DMA here with the same setting as the last one. We'll connect it to the light port to the GP port, and then the ACP port we will connect it to the AXI DMA, and we'll use the 100 megahertz clock. Okay, so then we will connect the another port S2MM to the ACP with the 100 megahertz clock. So this is the first step, like we did in the last time. Then we'll add the FFT. Okay, so for the FFT, we will use the smaller size FFT. Okay, so for FFT also we'll use the regular large size FFT compared to the last time when we used the 8-point FFT. So in the FFT setting, we'll use 1024-point FFT. In the implementation, we will use the floating point. We'll use the reset signal. And we'll use the natural order. Okay, so it is giving the error that the number of stages using the block RAM for the data and phase factors. Okay, so this is fine. Okay, so somehow it is giving the error. Let's figure it out. Okay, so the error is not there. So it is some bug in the tool. That's why that error is coming. Then you can see that you can connect the output of the FFT to the input of the DMA. And the input of the FFT to the output of the DMA. Okay, so the last thing is the configuration signal, which will keep it as a constant here for now. And we are using the 8-bit signal. Okay, so these connections are done. Let's see what it is saying. No, we don't need to connect the HP port. So we have connected this 1024.50 to the ACP port and to the Zynq SoC. So what we'll do is that we'll have another configuration of the ACP port with the shorter bus size. Okay, so I'll say that the ACP with the shorter burst one. So what I'll do is that in the burst size, I'll limit it to the only smaller one, that is 2. So ideally it should take more time. Then similarly, we need to create one more IP for the FFT. So this again, I'll write it as a shorter one. And then the output of this FFT is connected to the stream input of the DMA, and the input of the FFT is connected here. Okay, so let's do the run connection automation. As this we need to connect it to the ACP port, and this is also to the ACP port, S2MM to the ACP port, light to the GP port. So this is fine. We are connecting our DMA to the ACP port. Then the configuration signals, we'll use the same port for the 7th bit here, and the valid signal will connect it to the here. Okay, so this completes our ACP port. So we are considering two configuration of the ACP port, one with the short burst size and one with the largest burst size. Now let's move our focus to the HP port. In the HP port, we will do the three configuration. One is the HP port regular, second with the HP port with the maximum clock frequency, and the third with the HP port with the smaller data width. Okay, so I'll copy the DMA IP again here. So I'll first write it as rename it as a HP1. Okay, so now this HP port, let's do the connection automation. It is not giving the option for the ACP, so let's see HP, and then we can connect it to the HP port. Okay, HP0 to the HP port. So let's see now for this one, we should get the option for the HP port. That's we are getting. For the light, it should be a GP port. We are still using the 100 megahertz clock. Then we need to have the IP. So we need to have one more FFT IP. So that is HP. The output of this IP is connected to the output of the DMA is connected to the input of the IP, and output of the FFT is connected to the input. The configuration signals remains the same. You connect the valid signal to this one. So you can see that the valid signal is 16 bits. So we need to change it to the number of bits to the 16. And the data signal, okay, data and valid signal. Make sure we also connect the clock signal to the appropriate clock and the reset signal to the appropriate reset signal for all the FFT IP. Okay, so this is, we have done the HP port. Now we need to have the another HP port with the smaller width. So let's see another HP port. So I'll have the HP with the smaller width SW. Okay, so now this we will connect it to the our HP1 port, because HP1 port we have designed it to be the 32 bit. So let's connect HP1 port. We can connect the smaller width signal. Okay, so that is working fine. And then we can connect the so then we can connect the rest of the signal for this one to the HP1 port and for the light with the GP port. So this is we have taken care. Now the next thing we need to take care is we need to add the one more DMA for the higher clock frequency. Okay, before that we need to add the one more FFT IP. Okay, so this FFT IP is for the SW. Again, output of the DMA. Okay, so then the okay, so this is connected. Then the configuration signals T valid to the T data to the T data and T valid to the T valid. Okay, so that is done. Then the clock signal we need to connect to the rest of the clock and the reset signal. Okay, so I hope these things are clear till now. So now what we have done, we have used the four DMA, one for the small bus size in the ACP and one with the small memory width. We have not changed the memory width, so we need to do that. So here you can see that since I have connected the DMA, it is not giving me the option for the width connection. Okay, so we need to figure it out. So here you can see that the output of the HP1, it is 64-bit, and here it goes through the interconnect, and you can see here input to the HP1 port, you can see that it is 32-bit. So this interconnect takes care of the data bit conversion. You can also design the DMA with the input of 32-bit, and then you can add here between the IP, which is giving the 64-bit output, and this DMA, which will take the 32-bit input. You can add the AXI stream converter to convert that data, to do that data conversion. We will skip that process because this guy we have designed to work on the 64-bit, but here it will accept the 32-bit data. That conversion will be taken care by the AXI interconnect. Now, next thing we need to do is that add the DMA which works at a higher clock frequency. Okay, so we need to design a DMA which works at the higher clock frequency. Now, to avoid the clocking issue, because we have the already connected one to the HP1 and one to the HP0, let's add the one more HP port. Okay, so this is the HP port which will act as a 64-bit and it will operate at a higher clock frequency. Okay, so now this is the HP port, and you can see that now I have the additional clock available
which was there at a 256, I will be using that, and I have the additional port available. So now what I'm going to do is that I'm going to use this new DMA. So what I'm going to do is that I'm going to call it as a fast, because this is going to operate at a higher clock frequency. Now look at this carefully. Okay, so this operates at 64 and so on. Now I need to make sure that I use the appropriate clock for this one. So let's connect the AXI light. Now for AXI light, I'll be using the 100 megahertz clock because it will be, I want to make it work with the lower clock. It's a configuration signal. So that's not an issue. So I should be able to connect it. Now for the other ports, for example, for the HP port, you can see that I can connect it to the fast one. And here I can choose my clock frequency, that is 240 megahertz. Okay, so now I'm connecting the HP2 port to the fast DMA with this clock frequency, and now you can see that this clock is the clock which is coming from the 240 megahertz output clock. And you can see that now this interface is connected to the new interface for which the clock is coming from the other unit, okay, from the 240 megahertz. So you need to be careful here. Then what I'll do is that I'll do the rest of the connection for that fast DMA. Then here you can see that I am going to connect it to the HP2 port. You can see that automatically the clocks gets connected to the 240 megahertz. So I'll make sure it is 240 megahertz. Okay, so that has happened. Now I'll add the one more FFT. So this FFT, I'll call it as a fast FFT. Okay, so for this FFT, I need to be very careful. This FFT should work at a faster clock. So this FFT receives the data from the fast DMA. This FFT sends the data to the fast DMA, and this clock should be the faster clock, and this reset should come from the either the faster reset or the lower. So right now I'll connect it to the faster reset. Okay, so that is what I have connected, and the clock is connected to the faster clock, that is 240. So this FFT works at the faster clock. This works at the faster clock over the stream interface and memory map. On the light, it works on the lower clock. That is not an issue. Okay, so let's verify that if our design is correct. So we need to see that the ILA clock. So where is the ILA? Okay, we have not done the ILA connection. So let's connect the ILA to a slower clock. And let's validate the design. So we are getting one warning that we have not connected some signals of the fast one. I believe we have forgot some connections in the fast FFT. Okay, we forgot the data and the valid connections. So this is the data and the corresponding valid. So now let's validate. Okay, so the validation is successful. So all our connections are connected. So this is our complex design where we are using 5 FFT IP, 2 with the ACP, 3 with the HP port. In the ACP, we are playing around with the bus size. In the HP port, we are playing around with the memory map width, and we are playing around with the your clock frequency of the FFT IP. So then we do the regular process of generating the bit stream. So rest of the process we will discuss in the next video.